तो कर गए तो कल करें, नहीं तो कभी कर सकता हूँ,
कोई बात नहीं, करने की शुरू नहीं
वो तो करने को नहीं, लोगों को थोड़ा सा 5 मिनट गैप करने दो लोगों को। नहीं मुझे कुछ नहीं चाहिए।
No, you please start. Now time is running out. Time is running for lunch.
नहीं मैं इसलिए बोल रहा था, लोग ज़्यादा थक गए हैं।
पीपीटी तो नहीं,
No.
you can start.
Please start.
We are all fresh.
You're all fresh. I will make you fresh. Please start. Okay, so please welcome people and so on. So anyway, we start now. Okay, and I try to do my best. But you don't have to be afraid, because I will be talking very, very simple things and just some kind of conversation with you. Okay? So the topic that I have chosen is gravity, supergravity, and quantum gravity. So these are the topics that have been important for the mankind. I mean, some of them, the things that were known were important for the people from the very, very early times, right? People like, even in India, Aryabhatta, Brahmagupta too, and so on, and then coming all the way up to modern scientists, one after the other. You see, I mean, the very, very big names, I mean, Newton, Hawking, Einstein, everybody. So, our universe was born something like 13.7 billion years ago, and all the fundamental laws of nature were also born right at that time. And this is what we are trying to understand till date, and I believe the future generations would also continue to explore them, because it's never the end of the story. It's always the beginning. Whatever we know is too little, maybe less than 10% or maybe 1%. And what we need to know is still the entire, as Newton wrote, playing on the seashore, and the entire ocean lies unexplored before us. So at the moment, we have two fundamental theories at our hand. Two fundamental theories of nature at our hand: quantum theory and gravity theory. And both of these theories, they have been experimentally verified and tested up to several digits. And if you look at the list of Nobel Prizes, you find most of them going to this each and every little idea and topic in these two directions. So, in quantum theory, the beginning is the special relativity, which tells us the equivalence of mass and energy. In quantum mechanics, as Professor Nimai said, very important. In quantum mechanics, we have the possibility of creating energy out of vacuum, which is not empty, but is a boiling soup of particles being created and destroyed continuously. Many of you are teachers, many of you are going to become teachers, many of us, and all of us actually are also students at the same time. So you think of a simple one-dimensional harmonic oscillator in quantum mechanics, and you expand your x and p as linear sums of the creation and annihilation operators. So you have also not only these two, but also the preservation operator or the number operator, which is product of the creation and annihilation operator, right? So you operate on the vacuum state or n particle state by one creation operator, and you create n plus one particle state. Okay, in quantum mechanics, all of us do it. Okay, in quantum mechanics 1 we do it. At the university, some of my students are also sitting here. And so successively you apply the creation operator and you create particle states with larger and larger numbers. So what actually happens is that the energy eigenvalue of the state increases or decreases by 1 quantum unit of energy x cross omega as you apply the creation or the annihilation operator. However, if you apply the preservation operator, the number operator, which is A dagger A, then the n particle state remains n particle state. Okay? Because it does not, so you create 1 unit of quantum energy h cross omega and you annihilate it 1 unit of quantum energy h cross omega. And these three are being referred to in our, not only in India, but internationally by the theoretical physicists as the Brahma, Shiva and Vishnu. Brahma is your creation operator and your Shiva is the annihilation operator and Vishnu is the preservation operator. Right? So these are some basic issues. If you generalize your quantum mechanics to quantum field theory, so you talk about, let us say, very simple scalar field, vector field, spinor field, okay? And you make the Fourier expansions of these fields in terms of the creation and annihilation operators. And you always have these three things, creation, annihilation, and preservation operators. Based on this very concept, you can develop the entire theoretical physics right from not only mechanics, but also field theory, also string theory, also gravity theory, everything. This is what I want to convey to the younger generation, which I find is very, very enthusiastic and very energetic and very motivated also. So now, based on this very fundamental concept, you develop the entire particle physics. So this is the basis, the relativistically invariant quantum field theory. It describes the quantization of the three fundamental forces of nature: the strong force, strong nuclear force, weak nuclear force, and the electromagnetic force. And these three are being summed up very successfully in a theory called as the standard model. So many of you are working in that, people working in neutrino physics, people working in a standard model, strong interactions, and all these different branches. So all these three branches are being covered by that. So it describes the laws of microcosmos, to the universe inside the atom. And this is what we describe in terms of the standard model. Each and every step, each and every idea, all the predictions of the standard model, they experimentally stand well tested up to several digits. Okay? And its conclusion that the particle content of the standard model is you have 6 quarks and 6 electrons at your hand. So up, down, string, charm, Newtonian top, and electron, muon, tauon, and their corresponding 3 electronic, tauonic, muonic neutrinos. Some of you are doing it very, very actively when you know this, and I understand that many of them are doing particle physics, but I would tell you that we need much more than the particle physics people. We need almost everybody, all branches of physics. So as you proceed, I will tell you how and why. So now this is one thing, and of course, in addition to quarks and leptons, you also have the carriers of these forces. We are, let us say, 200 participants, 100 participants, but how do we talk to each other? How do we interact with each other? This is what the particle physics does, and it is being successfully done in terms of the Feynman rules and the Feynman diagrams, so that the pictorial way of representing the interactions of how these elementary particles talk to each other. And all these three fundamental forces of nature are being extremely well successfully described in terms of the so-called standard model. Now we look at another thing called gravity. which is also right from the beginning. We know something drops out of my hands, it goes to the ground. So it is the most obvious force that the mankind had ever known, the gravity. Okay, mango falls down. You don't have to necessarily make apple fall down, but mangoes also fall down. It will go to the ground. So even a farmer knows that the mango will not go up but will come down. So gravity is a very, very obvious force. It's the weakest of all the four fundamental forces of nature, but it is the most obvious, right? We observe it all day and night around the clock. So this is very, very important, and one would like to understand. All the Rishi Munis and scientists, they have been trying to understand this phenomenon of gravity, and it describes also cosmos, but the advanced scale. Physics of the cosmos, physics of the solar system, physics of the black holes, physics of the wormholes, physics of the time travel, and so on. On each of these topics, I could very easily give 1 hour or 2 hours talk, just with a microphone in my hands. So these topics are very, very fundamental, very, very important, not only to particle physics, but to the entire mankind. Now, I tell you one very, you might be feeling astonished to know this. Gravity theory, the most successful theory that we talk about,